Yeah.
But I guess.
Okay, I'll go back. I'll have to wait. I'm off.
So I guess she's gonna use this one. So did you see the email mailbox?
Let's see it yet.
You got it?
Yep.
No.
Yeah.
Yet.
Yeah, I see Scott is online.
Let me just go.
Yes. There you go. Correct.
All right.
Let me just talk to you over there.
Can you hear me,
Yes.
Yes.
Can you hear us?
Rebecca?
Yes.
Oh, good. Yes, I can. So this is working, but the people who asked to be on, it said they weren't online, so I'll email them. No, I did email them. So, okay.
Scott talking?
He was
Yeah.
talking.
Okay. It works.
All right, we have one new visitor. That's Sun. Do you hear us, Sun? Okay, I'm coming over.
I was wondering if you decided to watch it.
I know.
What amazing. We managed to get a whole crowd of people here before 2 o'clock. That's really rare. It shows that nothing else is happening, I suppose.
Awesome. Thank you.
And of course, the illustriousness of our guest and her fascinating topic. We also have one remote login person. And a second one had asked to be included and now has the invite. So let me just start with a little introduction to give it, so it'll end in 4 minutes at 2 o'clock. We should wait for it. And I'm Scott McCaig. I direct the Swartz Center across the way. For Computational Neuroscience. And Ziping Zheng is the Associate Director. And some of the people here are work at the Swartz Center. Others I recognize from UCSD and a few from off campus. So this is about 10 days ago now. Has it been that long, John?
Yeah,
It really has.
exactly.
It's hard to believe, as I just feel exhausted still thinking about it. But we turned in a application to UC MRPI, Multi-Campus Research Programs and Initiatives. UC itself in Berkeley wants to encourage new areas of research interactively between campuses. So I thought, well, music and brain, what I started calling in the proposal music, mind, brain, and body research, was only done by isolated faculty members in this department or that department across the campuses. And since both John and I had a chance to meet 2 such faculty members at the UC Merced and UC Davis, as well as UCLA and other places. We thought that we should put in something for music research. So after great effort, we came up with an acronym, and that was UC-MERC for Music Experience Research Community Initiative. And so we sent off that proposal. It would be a planning proposal. It would have a couple of conferences. It would have a quarterly research series that would be broadcast by YouTube to other campuses, and that would rotate between campuses. And then there would be a kind of a culminating yearly conference and workshop to plan for further proposals, both to UC itself and to other agencies. To really find out whether we can, in fact, realize the glorious vision that we put forth in the 5-page grant that UC could become a leader in an area of study that really doesn't have a center devoted to it in the United States. And that is this very complex, high-level, and both psychologically and economically important activity of music. So in the invitation, I christened this the beginning of the first seminar. Please come in. We're delaying for time here a little bit. Here, take this chair. So I called this the announcement or the kickoff or something, seminar for UC Mercy, and I'm happy to introduce our first speaker. Rebecca Schaefer is from Santa Barbara, and you'll be amazed to hear that she's a native Dutch speaker. I still can't do that. But she has a lot of American experience now, and she's been working on in areas related to psychology and music and brain for several years in Netherlands, in Edinburgh, Scotland, and now in Santa Barbara. So, welcome, Rebecca.
Thank you. Take the chair. Okay, well, thank you all for coming and for inviting me to give a talk here. I want to tell you a little bit about the fMRI work that I did while I was in Edinburgh, which focuses mostly on measures of cued movement. Yeah, let's see if this works. Right. So moving to music, really, I don't know where I'm going to stand here, is quite intuitive. We all know this. It's a sort of, we know there's this intricate connection of music and movement, and it happens quite spontaneously. You don't really have to learn. You might have some other, visual or other things happening, but we know that this music is giving this really strong inclination to move. And although we can do this by ourselves, like the iconic sort of iPod commercial, but also of course in groups. And we use musical rhythm to coordinate, to do things together, which can be just to be more effective or also just for fun. And a lot of this movement and music connection is also backed up by neuroscience. And fMRI findings have shown us for quite a while that the networks used to perceive rhythms are actually overlapping with the brain areas that we use to move. And already more than 10 years ago, Ricardo Schaefer was using these results to consider motor and rhythm perception networks as sort of commonly coded for timing mechanisms. And later, Jessica Grahn, among others, did a series of studies showing that there are a number of motor areas that are specifically important, involved in perceiving rhythms and the presence of a beat in a temporal pattern. So whether we can extract some sort of higher level regularity in a rhythmic pattern that leads us to feel a beat. And Joyce Chen and co-workers also added to this literature some findings showing that the more complex the rhythm is, she's finding more premotor activation in the more ventral areas. So basically, to give you an example of the kind of stimuli that people use for this, I've stolen some from Jessica Brown's website, where you'll hear an example of what she considers a rhythm with a very obvious beat. Okay, so, and then she also had stimuli with a slightly less obvious beat, but still with a sort of an extractable higher regularity. But then also stimuli that didn't have that type of regularities, where you can't really make these larger periodicities. So I hope that makes it a little bit more clear what kind of stimuli people are using in this type of work. So when we think about entrainment and moving to sound, like, of course there's already some sort of perceptual entrainment when you listen to recurring rhythms. From dynamic attention theory and Mary Jones' work, we think about this as sort of fluctuating attention levels, where you get more in, where your attention is drawn to specific parts of a periodic pattern. And we call, and this is a big part of what's called beat induction. And then when in the motor domain, the phase synchronization to a rhythm is relatively automatic. And so exercising to music has been reported to lead to reduced perceived exertion, and also, of course, synchronizing with others facilitates joint action. If you want to lift a table together, you have to make sure that your time is going to be right. And so for this type of thing, temporal prediction is really important. So Bruno Rep, in decades of work, has shown that we tend to do this in a predictive way. If we tap along with a metronome, or generally a little bit early, which is indicative of predictive processing. And this has also been echoed in brain findings showing that we have different brain responses to accented and non-accented rhythmic events, even when we're just imagining the accent. Okay, so I'm interested in this mostly in the context of movement rehabilitation, and of course for music therapy, it's been a long-standing tradition of seeing how music can help people feel better just by exposing people to music. But more specifically for movement rehabilitation, we have there are a number of cue training paradigms, so walking to a metronome, or which is specifically shown to be helpful for people with Parkinson's, but also stroke upper limb movement, for which elaborate mechanisms are built to really constrain how people move and to make sure that they're practicing in a specific way. And when we think about why cueing might help movement learning, there are a number of things that we can think of. So one would be that it simply speeds up the learning just by having the affordance of many repetitions. So music is interesting in the sense that the many repetitions that it has tend to not bother us, not in the way they would for language anyway. And so it basically has an affordance for doing a particular action many times, which is still sort of the best predictor of recovery and of learning. Now, another possible mechanism that's raised in the literature is that it might qualitatively change the way we learn, right? So by embedding a movement in an auditory environment, you're enriching it and you're creating more connections, or you're somehow changing qualitatively how people learn. But there are also some recent findings that just temporal training, moving rhythmically, has carryover to other functions. So recent studies showed Parkinson's people who were walking with a metronome were then also able to perceive temporal changes better after this training. So somehow the increasing temporal skills might have effects in all sorts of different ways. And finally, what's actually named most often in terms of music therapy is the affective mechanism. So the engagement we have with music, the way it lifts mood and adds motivation. And so I've discussed these different mechanisms in a paper that's coming up pretty soon. So for the current work, I was interested in how music affects the motor network activations during movement. So the previous results that I showed were just perceptual, people lying, well, with their head in a big magnet, listening to rhythms. So what happens when you're actually already moving? Does the music somehow change the way motor areas implement that movement? And I was also interested to see whether this effect can be reduced to simply the beat. So mostly in movement rehabilitation, people are using metronomes rather than music. And so does that lead to a similar type of effects? And again, purely within the motor network. And then finally, so a lot of my previous work was on music imagination, and I was interested to see whether when we imagine music, can we create that cueing effect cognitively? Can we basically create the time structure with our own imagination that would somehow support movement. And there are some reports of people using Imagine music in rehabilitation situations, but it's quite scarce still and somewhat not very experimentally controlled. So when you consider some of the previous findings of directly comparing cued versus uncued movement, well, we know that from Michael Taut's work that if you have complex movements with long trajectories, the cueing will actually regularize it and make, for instance, a reaching trajectory more smooth. Now, in brain imaging, I don't know, some of you may be aware of this study where Stephen Brown had people do tango steps while in a supine position. Basically had them do quite complex, or anyway, not really straightforward, like these are all tango experts, steps with a natural music stimulus, namely tango music. And when directly comparing doing those steps to music versus doing those steps without the music, he only found some cerebellar activation for the cued movement as opposed to the self-paced steps. But then more recently, another study came out where people didn't do complex dancing steps, but rather just moved their feet like this while lying back while watching a hallway, so as to sort of simulate a walking experience. And this was actually done with a metronome and not with the natural music stimulus. But there the authors found that actually there weren't any motor network areas that were more activated for cued movement, although for self-paced movement they were finding more basal ganglia, which is kind of unintuitive for a lot of rhythm researchers. Now, an even earlier study did use cued and uncued wrist flexions in the scanner. They didn't directly compare statistically the cued and the uncued. They were just different parts of the study, but they sort of qualitatively said in their paper that the cued movements elicited smaller activations than the uncued, naming this as sort of a facilitation effect, saying, oh well, if you don't have to create the timing yourself, this supports movement. So what we have is a set of kind of conflicting results, but also different movement complexity, different kinds of cueing stimuli. So there's it's not yet, you can't really get from this what you would expect as a cueing effect. And now I was, as I said for the research questions, I was interested in the effects of the different cues. So we decided to keep the movement really simple. We used the wrist flexions as in the study I mentioned last, only bilateral. And so I was interested in looking at metronome music and Imagine music. And so for a metronome, we know it's very regular, it's unambiguous, it's very repetitive. Might, it just make things, make movements a lot smoother. So there's also from sports science, there's a study recently that suggested that running to metronome is actually makes movements more efficient than running to movement. And we know that this rhythm perception, it engages the motor areas that I mentioned before, so putamen, premotor cortex, supplementary motor areas. Whereas when you move to music, when you get to music, it's a more complex and layered stimulus. There's possibly more ambiguity about where the beat is, but there's also more potential for affective engagement and more, more emotional response. And again, from previous literature, we know that a number of motor areas are engaged. Three motor areas: basal ganglia, cerebellum. And finally, Imagine music. Well, we know that Imagine music and heard music overlap to some extent in the brain, although the extent to which might vary a little bit depending on the stimulus. But from fMRI work, motor areas have consistently been reported to be involved. So mostly SMA, supplementary motor area, but also in some cases premotor or striatum or cerebellum. So we know that in all these stimuli, the motor areas are already involved, but none of this is in the context of moving. So what we did, we made two separate fMRI experiments. So we assessed the cueing effects for simple movements, comparing uncued performance to metronome cueing, where we had uncued movements, metronome cued movements, and then an auditory control condition, people just lying back and listening to the metronome. And then we had, in a second experiment, we had used music and imagined music cueing. So there, again, uncued movements, music cued, and imagery cued movements. And the stimuli we used, this was our metronome, so pretty straightforward. I personally like metronomes with an attack time a little bit more than beats, but that's, I don't know. Sorry? Yeah, it's a MIDI woodblock. Yeah, it's not very advanced, but it was what I liked for this metronome. And the music stimulus was this. So basically people are lying back and they're moving their wrists. Make this to the very end of it. And so for
clubs in Edinburgh.
Everybody's doing it these days. Yeah. So for the imagery before the experiment, we had them listen to this fragment and until they said they could imagine it. In the basically when recruiting people, we had already said, like, we're gonna ask you to imagine music. So they knew that they were. They said that they were able to imagine music even before they arrived, and then when none of them needed more than 5 or 10 minutes with this. They got the pretty fast. And we selected this particular piece of music for a number of reasons. So one, that has more rhythmic things going on than the metronome, obviously, but also it has voices but no words. It's sung in both a male and a female register. So the melody is sort of easy to hum for everyone. So we thought that those were a few. And then the tempo is fits with the most common dance tempo based on previous literature. So our hypotheses were that, in line with the finding of more complexity of more premotor cortexes, that for the music we would find more premotor cortex activity than for at least for uncued movement, and that for imagery that we would find some sort of equivalence, that we would find something similar to what's happening with the music, both in comparison to uncued movement. Now, for the cueing effect itself, there's some, based on these conflicting previous findings, there's some competing ideas. So if you would simply think that the motor network activations of rhythm perception would sort of come on top of the motor network activations of actually moving, and it would be some sort of additive thing, then you would expect basically those motor networks to be more active for cued movement than for uncued movement. But what's a little bit more likely would be that if the rhythm modulates the movement somehow, that you, for instance, would see the cerebellar activation that Stephen Brown found, and possibly also something for self-pacing the movement, as the Toy Moore study showed. So in these experiments, we had 16 and 17 non-musicians. It was a block design, so basically they'd get these 16-second blocks of moving as they get their instruction. So this is the block that's going to come up. They had a little timing, a little tempo cue, so that if it was uncued, they would move at roughly the same tempo. But the tempo cue was there for every type of trial. And we basically we did our analyses within a mask of the motor networks that we were interested in. So we didn't look at auditory or these other areas, just to focus really on how the movement is modulated. And we also repeated the experiment outside of the scanner, basically having people lie back, moving their hands, but attaching a single motion capture sensor to one finger just to see if there are like huge differences in how they were flexing their fingers or their hands. But let's see, this is what's happening. So there's a picture I took from the FAO 2004 paper, so that's pretty much how they were lying back with supported hands, only bilateral. And the motor mask was BA4, so a precentral primary motor, BA6, which covers most of premotor areas. Striatum, motor nuclei of the thalamus, and the whole cerebellum. And the behavioral experiment group was a little bit smaller than the fMRI. So I'll first show you the results from the behavioral. Basically extracted some really basic aspects of the movements, just the number of flexions, the mean range of the flexions, and the mean velocity. And there weren't any differences between conditions. I'm not sure you can see this, but every first column is moving to silence, then moving to metronome, moving to music, then moving to imagery, and they're pretty much all the same. Now, there could be that there are like more subtle things happening that we're not getting with these measures, but we explicitly chose a very simple movement to try and keep that the same while we're looking at what the brain's doing. So we were happy to find no differences there. Moving on to the fMRI results of the metronome cueing. I'm not sure you can see those little orange dots here, but what you're seeing in this row are slices of the metronome cued greater than self-paced movement. So basically looking at what's activated for the metronome, what's more activated for the metronome. And what you're seeing is one cluster in left precentral gyrus, and bilateral clusters here in the middle superior frontal. And the graphs here are showing you the parameter estimates for the fold activation in those at the peak voxel of those clusters.
Could you point slowly to the?
Yes. So these are the slices through the brain, right? So this cluster, this is the same cluster here, and then there's two here that are extending more. Yeah. And so here the white bars, the self-paced movements, the slightly more gray bars, metronome cued, and then the darker gray is a listening control condition. Because what we wanted to see is whether the areas that were more active for cued movements were just activated by listening, or at least also activated by listening. And so you see slightly. So this one is pretty straightforward. This precentral gyrus is just showing more activation for self-paced movement, which is not due to listening, because the listening condition is not showing that activation. These two are slightly more puzzling, but because what you can see from the parameter estimates is that there's positive difference, basically because the self-paced movement has a negative fold activation, which leads to what we would see as a positive result. So that's is something we're working on right now. Basically, in words, what we're seeing is this increase in left precentral gyrus activation, but a lack of decrease in the bilateral superior frontal gyrus activation. So extra motor involvement on the one hand, but this superior frontal gyrus area suggests these areas are known to be part of the default mode. So basically, because we're only looking in the motor network, within the motor network, I don't have the data right now about what's happening in the other default mode network areas. That's something that I'm in the process of doing now. But if that pans out, it actually would be an indication of decreased effort for the cued movement. Yeah.
So, I mean, your stimuli are 2 per second.
Yeah.
And the movements are 1 per second.
Yeah.
But frequency content. fMRI is a low-pass signal, and it doesn't have much of its energy at 1 hertz. So what was the temporal contrast? At what points did you measure the activation?
So basically, in a block design, you're taking the full 16 seconds and sort of looking at what the bulb activation is over that whole period, right? So at least that's what goes into the model.
So was there any time? Did you look at the time courses in those areas? Related to the music?
Well, we'll get to the music next, but
Well, these are just
this is just the metronome. These are just the metronome results. Yeah, maybe I'll show you the music results.
Was there anything related to this?
No, I didn't see it. I didn't see it, but also I didn't run a model that would look specifically for that yet. Finally, we know that at least with the control condition, that the activations that I just showed you here, they're not due to listening to the metronome. And we're also not replicating the study that we based our movement on. We basically just found something else. Of course, that was an early days fMRI paper, so that's perhaps not very surprising. Well, and their objective was never to look at this specifically. So moving on to the music and the music imagery, I actually see quite a different set of results. So here you see, this is actually what I should have said here is that we saw nothing related to self-pacing. So if you have self-paced over metronome cueing, there was no indication of that. Which is also the case for the music experiment. Again, we only see activations of cued movement that are greater than uncued movement. And for the music, this is specifically in the left cerebellum 6, which is an area that's previously been implicated in music perception. And for the imagery, it is the right pallidum and the SMA. Now, again, interestingly, if you look at the parameter estimates, you see here that actually this area in the imagery is pretty much just as activated, but it didn't reach our cluster threshold for significance. So there's, it doesn't come up as significant, but we can't really say anything about, I mean, we can't say that it's not active. And similarly, for the pallidum activation, we see almost like a linear incline there, where the music is doing something, it's just not enough to become significant compared to the self-paced movement. Whereas when you're looking at the SMA, which is the region that was most consistently implicated for music imagery, and you see that compared to both music and self-paced movement, it's just very different. So that is an indication that it is quite specific to the imagination aspect and not so much to the movement. We did also compare music and imagine music directly, just to look further at this equivalence hypothesis. And actually, the SMA results returns is still there, so that's good. It confirms what I just said. But we get some other cerebellar areas that are more active for music cue movement than they are for imagery, and that we didn't have direct hypotheses about that. So I can only sort of speculate a little bit on what that means. And these are different areas than the cerebellum 6 that we found in the music over uncued movements comparison. But the chances, I mean, there are some indications in previous literature, not to go full reverse inference, but there are some indications that these are areas that are related to perceptual regularity or perceiving regularities. So again, in words, the musically cued risk flexions led to increased left cerebellum 6. The imagined music cues led to increased right pallidum and bilateral pre-SMA. The direct comparison of the cues doesn't reveal any difference in cerebellum 6 or the right pallidum, which are the main findings for two conditions. However, SMA is uniquely activated for injury. Now, regarding these areas, cerebellum 6 is pretty consistently reported to be involved in auditory and motor coupling, and of the other regions that are implicated in music and rhythm perception, it looks to be behaving differently than the other motor areas that are involved in rhythm perception. So for some reason, in the context of movement, this is an area that continues to care about preceding rhythms rather than free motor or even basal ganglia. And we're not replicating Stephen Brown's work here, which is the only other study that uses natural, or the only study I'm aware of that uses natural music stimulation. Okay, so because we did this in two separate experiments, we didn't directly compare the metronome and the music cueing, but we do see sort of a distinctly different pattern between the two. And so the premotor and precentral activations may suggest more sort of fine-tuning of movement, and with the metronome trying to be on time. I mean, this is still speculative at this point, but the cerebellar activation appears to apply a more automatic, more natural type of movements, which, although that seems to be intuitive when you compare the metronome and the music stimuli. The music and imagined music are not shown to be different. They're not exactly shown to be the same either. So, absence of significance. But it seems like they might be implicating the same motor areas, but to somewhat different degrees. Now, I'm specifically very interested in this pallidum activation for its clinical relevance. So, the pallidum is one of the two main stimulation sites for deep brain stimulation in Parkinsons, the other being subthalamic nucleus. So it's kind of interesting that, and to be fair, this whole idea from this study came from working with Parkinson's patients who were saying that they were much better able to walk and just do their shopping and everything when they were imagining, songs from their youth or war past in this case. So it does seem that in some cases it can help people. It's just trying to sort of get a handle on what's happening. So I was pretty excited to find this pallidum activation. So for the rehabilitation context, what it looks like is that different cues impact the brain differently, and that different patient groups might need different types of cues in order to support their movement. And so we already see this from, Parkinson's people seem to be fairly well supported by cues in a lot of cases, whereas Huntington's disease patients have a lot of trouble synchronizing. And there were some initial reports that it seemed to help, but more and more papers are coming out where it's just really hard for people to find the periodicity of the cue to move with, or to maybe not find the periodicity, but to actually move with it. And interestingly, Alzheimer's disease patients were fairly recently reported to actually have worsened gait when they're trying to walk to either metronome or music cues. So that the implication there, I think, is that there's more attentional processing going on than we think it's all very automatic, but aligning your movement to sound does require some maybe more cognitive abilities that the Alzheimer's patients might not be able. Interestingly, very recent paper showing that for stroke patients, the stage of their impairment had an impact on how much the cue was helping them as well. So even within one patient group, although strokes can hardly be called one patient group, but even within within one medical problem that you're trying to solve, namely in this case, I think it was gait, either gait or upper limb. They were showing people with very mild impairment to benefit much more than people with serious impairment. So, which is also somewhat intuitive, but it's good to keep in mind that both the type of neurological problem as well as the stage or the degree of impairment are important when thinking about these things. And so the findings that I have, which come from healthy, mostly students, they would need to be replicated in these different patient groups and applied to different types of movements as well before we have a better idea of how to help patients with this. And so I want to thank my collaborators on this project, so namely Katie Overy, who hosted me in Edinburgh for the time I was there with the Mary Curie Fellowship, Alexa Morcom in psychology, and Neil Roberts with the clinical research and something. Are there any questions?
I just have a comment. I've been doing something called neurofeedback, and I'm having my Parkinson's patient work for people. So it's almost like they're creating a metronome.
Right.
So it kind of put a light bulb on in my head, because the more successful they are, the more beats they get. And it sounds like a metronome. I'm thinking that with this consistent beeping going, and they're leaving my office, getting out of the chair faster, and moving better. So.
And what are you training them to do?
Area,
so more beta or
more
okay. Okay.
You can't do more beta with tremor, but
sure.
People with like estimation, like kinesia, beta.
Yeah.
It's pretty amazing the metronome.
Yeah, and it helps some people, and I mean there are some. So there was a relatively small, I think, survey study published recently, also from Jessica Brown's lab, where they were asking Parkinson's patients, does their enjoyment of music change? Has it changed since their Parkinson's? And none of them really felt that. So it's not like the rhythm makes everything better, but for some patients it seems to assist their walking. Now you probably know this, but if you draw a set of lines on the floor, that already helps, right? So it doesn't apparently necessarily need to be auditory structure, but just sort of cues and structure more generally. It's just that the auditory system is so well equipped to detect these regularities in a very precise way.
But there's a quick question. Freezing the gait.
Yeah. Yeah.
Most of my patients have to set sideways. Yeah, that was to break them. Do you have any clue why that is? Because I do the lines on the carpet, but it's sideways. Turn their body sideways and then break.
I don't know about the spatial attention. I wouldn't be confident to comment, but I do know that it seems from one or two studies, it seems that the freezers are responding differently to auditory cues than non-freezers are. So again, Parkinson's can be quite a collection of, yeah, exactly. So I mean that's really interesting. I hadn't heard that before.
Yeah.
Thanks.
You just get through a threshold and turn sideways.
Yeah. Yeah. Any other questions?
So I have go ahead. Okay. I mean, so we had 16 subjects, I think?
Yeah, 16 and 117.
Do you think we need more to really get to the bonus of these things? It seemed like some of the effects were small. I just wonder how much heterogeneity there is among people. I don't know if you can quantify that, or you have an impression of that from your data. The individual.
Well, I mean, more would have been better. That's clear. But I think so aside from the brain data, everybody seemed to like the experiments, which was kind of interesting to me because you're doing something really boring. But I mean, I think some of them were also just excited to see an MRI scanner or something. But I had them fill in imagery questionnaires. So how good and they were slightly better than the average for normative data. So we had sort of pre-selected already people who have that skill or you know, have that behavior naturally. So that's already a pre-selection that might, you know, do something. But I think that in terms of how homogeneous this group was, I don't have an impression that there's really like a sort of a, like there's two types or something like that. I mean, I'd have to look at it more specifically, because basically what we tried to do is just really narrow it down to the hypotheses we had and look specifically in these areas. But of course, like there's so much more brain to look at. In that sense, I think there's a lot more to be done. Also in terms of connectivity, because that's really what that's, to be honest, I think is what would be a good next step for this superior middle frontal finding, to see what it's connected with and what it's doing. That still doesn't answer your question about the homogeneity of the group, but yeah, no, I don't have the impression that it's all over the place. They seem to be doing the same thing.
It's certainly interesting to me that the supplementary motor imaging question was always thought of as a motor planning area.
Yeah.
Here it turns out to be a motor imagery.
Well, music imagery, yeah. So sequencing, that sort of thing, has always been sort of classically put in that corner, and I think basically everybody by now agrees that supplementary motor areas are doing lots of stuff.
Yeah, but of course, when you're imagining music, you're imagining sequences.
Yeah.
Even if your dance stuff is stereotyped.
Yeah.
I imagine that anyone on the imaginary dance club who is doing this would actually modulate the actual movements themselves, the dynamics of the music, to the sequence of the music.
Right. So you think there are differences in the motor output that would be related to
No, so the music imagination and the motor planning in this case would need to be separate. A tangible relationship, or certainly it might come out more if you look at.
Yeah, I actually had to stop people from like moving their feet. Sorry, I think you were first.
Do you know there's any relation between the hand movement and the activity?
I didn't find any severe head movements at all. I was surprised, to be honest. So I think this is because of all the padding that we used to make people like to have their arms be really relaxed. Because if this part can relax, then you can just sort of move your wrists independently. We had, in a completely different study, we had a girl singing opera in the scanner, and she found that like pushing her head into the pillow would basically make her body go down instead of her head go up when she took a big breath. So the people developed these little strategies to we've never taken people down or things like that, which it happens. But I was honestly I didn't have motor artifacts movement artifact problems with anyone. Now we also had a Siemens scanner that has part of that internalized, so it already does some automatic motion function.
Yes, it is from a musician point of view. Did you do any experimentation with polyrhythmic metronomes? Did like multiple phasings gave more activity?
More activity?
Well, more brain activity. It's a higher structure of pulse.
Or maybe John would be more in a better position to tell you about that. I haven't done any of that kind of work. Also, because I was interested in what happens while people are moving, so I tried to make it relatively simple for them, especially since they were non-musicians. I guess my thinking was mostly based on how does sound support or somehow facilitate movement. I think if you make it, if the sound is more complex, it might be more rewarding, the movement. I don't know, that's maybe my own intuition, but I think in terms of complexity of the rhythm, well, there's many ways in which rhythms can be complex, obviously. But in terms of these short rhythms that were used in previous fMRI studies, it looks like whether people can extract the beat is important, and well, to a certain extent, just like how many events are happening. And to what extent they're always like on beat. And so a lot of people have been using syncopation as a sort of a proxy for complexity. So I mean, I think Peter Voest has done some stuff on polyrhythms. So there's a Danish researcher who has done a little bit, and what he showed is that actually for the more complex rhythmic things happening for musicians, he found a different levelization than for non-musicians, sort of implying that the skill level impacts, you know, the I don't know how precise you're thinking about it. But I haven't done any of that.
John?
I'd like to know the answer to that question too. I think you summarized what I know certainly.
Okay.
Yeah, there's definitely there's some work on whether we could actually hold multiple beats in mind at the same time. So whether, you know, there's always the question whether polyrhythm is represented as two separate, you know, rhythms in different tempos, or if it's represented as a higher order metric structure. So Scott has an experiment where it involves switching between different meters. So I think that starts to get a little bit of that. But as far as I know, most of the evidence I've seen is it's very difficult to have two beats in the at the same time.
Yeah. John?
For Western listeners. Yeah, I guess that's true.
Well, it depends, yeah, which music approach you have. But John, can you summarize a little results of that? Metrical modulation experiment. It wasn't at the same areas pretty much that she showed.
Yeah, it looked like it. So it's a metronome pacing, and people are switching between the kind of simple 4/4 rhythmic reproduction and something in 3/2. So they're switching at predictable times between these two kind of outputs. The metronome is always the same, but the rhythmic outputs. And so what you see at those change points is kind of a burst of activity in that same frontal area, you know, suggesting that has something to do with, for example, in a polyrhythm, switching between two different levels.
But at the same time, the SAMA, something here it was polyrhythm.
Yeah, there are other sort of more motor areas that are just simplified in the beat. So it's tricky with this because if you look at the motor areas, you see the beat very clearly because you know people can move along with it. The question is, where did that idea come from? Where was that pattern that it generated with that skill?
So again, the connectivity between them.
Yeah. Yes.
We were using, of course, EG to look at that.
Well, yeah, and but the one thing there, I mean, because in my music studies with EEG, it looked like a lot of the frontal things that were happening were projections from auditory areas, which is, I mean, this sort of strictly speaking, auditory and one will always be sort of frontal central, right?
But we're talking about this.
Right, right. But I was also interested to find that for our metronome listening condition, which is really only a beat, like there's nothing else, we didn't find the basal ganglia findings that Jessica Brown had. And I spoke to Jessica about it, and she really wasn't surprised, saying, like, oh, this is 16 seconds of one thing. She's doing these short rhythms where she's doing same different discriminations. So you're hearing short rhythms and having to think about them, which is really, I mean, with the metronome, you don't have to like spend a whole lot of attention on it, or at least a healthy brain might not have to, right?
rhythms you're using, or are they just sounds like examples, loops? Even as a musician, those don't react to those rhythms.
Right.
I have to,
Right.
I listen to a tap.
Right. Yeah. Yeah. Well, I have to agree with you there. So I'm to be honest, I'm not entirely sure why I should trust to do it that way. But I think there is definitely a profound difference between listening to a metronome for 16 seconds and judging these short rhythms for distinct qualities, either same, different, or I think she also did it versus what I had to say. How easy is it to move to position something being related? So and the not finding basal ganglia for rhythms of long duration is now also coming out of the so that people are finding this. So I mean, it might be that this is either only a short-lived response, or it's something to do with the attentional aspects of listening to short rhythms.
You usually have some kind of pattern that suggests it's the finding the beat that
Yeah,
involves
as
the
opposed to
basal ganglia
tracking
as
it.
opposed to maintaining it.
Yeah, but still, these were short. These weren't like really long, sustained.
The metronome.
Yeah.
Yeah. Maybe, like you said, it wouldn't take very long to find.
No, especially since you're already cued in for the rhythm.
Yeah.
So in the model I used, I basically took the preparation out. Right, I'm just interested in what happens during that block. So when people are getting the cue to start moving, which is pretty much when the tempo is established, that activation is not in these blocks. Yeah.
And the tempo is the same across
Yeah.
blocks too. So.
Yeah. There's nothing changing, right? Yeah.
Is the cerebellum activated?
No. What I found basically is really all the auditory areas, at least for these long stretches of metronome. Yeah, I was a bit surprised, to be honest. I thought there would be more, but maybe like a time varying, like a tempo varying metronome, and I suspect it would be very good. So,
I'm just kind of thinking about it. I realize other studies are very sorry. So it's kind of like
yeah.
hearing or imagining brain.
Right, and then move into it.
Yeah.
So I thought a lot about this actually, but what most of it ended up as, to move to a non-metric stimulus basically becomes sort of a reaction time task, right? And you're just, it becomes something different, or at least I thought different enough to not warrant, this direct comparison with I think in Stephen Brown's study, he tried something like that, where people had to move to like unpredictable, like, yeah, I don't. Yeah, but the thing is, like, if you would move to imagine gunfire, right? To follow your example, like, how would you? Huh? Fireworks. Popcorn, good. If you like popcorn. It would basically become one of these sort of volition tasks, like move whenever you feel like moving or something, right? And I didn't feel confident that the type of entrainment that I was interested in was a part of that. But it's an excellent point, and I have thought about it. Yeah.
Well, you said you were recently at the World Cognition and Music Conference. For those of us who haven't been to those conferences, how would you place this research in the lab among other research, say, on rhythm that you might attend?
Well, there's a lot of research right now on musical movement, and it sort of falls into two broad categories, one being healthcare oriented and one being music performance oriented. I actually, at the conference, hosted a symposium trying to contrast, how entrainment supports music versus how getting auditory feedback from your movement supports movement learning, which is obviously both happening when you're making music, right? You're having these sort of forward and inverse models going at the same time. And not a lot of people that was actually the point of the symposium, was to sort of pull together some of these findings. I think it's a very, there's a lot of research interest for this right now. Not so much brain imaging, somewhat more on perception than on action. A lot of nice motion capture studies. So there's more and more motion capture on dance, which is very interesting and fun to watch.
But I suppose another conclusion would be that in fact, indeed, the studies in brain imaging and music are still really
Yeah, but it's not it's not easy. So the scatter noise, the movement artifacts, like there's all these things that make this a highly unnatural listening situation, and there are so many ways in which you can look at more, more relevant behaviorally more relevant situations. So I think the brain imaging can only serve as sort of a backdrop for what we see people and everyone doing in real life. And I think in terms of the healthcare applications that it's important that we figure out what the cerebral mechanisms are. But you're always going to be limited to, something very restricted. And so
if you use fMRI.
True.
If you use EEG.
True. But so the idea that was the Huntington's and Parkinson's patients who both had basal ganglia problems, but respond really differently. I mean, that also, I won't say that rhythm research will teach us about, what's going on with these patients necessarily, but it does add to the picture of, the different, like subtle differences in neurodegenerative disorders and how we can try to help people with those.
Very weird question.
Go for it.
So, what I understood that consciousness occurs at 300 milliseconds, and when we are listening to music, when I play my flute, I know that I hear the sound much faster than that. I'm conscious of the sound much faster than that. And so I'm wondering, what's the deal here? Can we actually be conscious of super fast things?
Well, we can detect timbres and like short fragments of music, like with only 30 minutes, something like that. But you don't probably have that realization in those same 30 milliseconds, right?
But we control power. Yeah, maybe we control it unconsciously.
Yeah.
So we're having control.
Yeah, I think. Well, of course, like this is not a hard number, but like, let's say 80% of motor control is largely automatic, right? We don't think about most movements that we carry out. And in this case, I think that the auditory stimulation that somehow traps the movements because it has this really strong tempo structure. But we don't really know how that would happen. I don't know. I don't think I have a better answer for you.
All right, well, let's thank our speaker again. And invite those who would like to come over to Swartz Center for tea. Again, as soon as I heat up the
So should I?
Do you hold them down?
Yeah, you love me off.
Okay. So